Okay, so I'm going to talk about learning about the physical world, or maybe the informal subtitle about the game engine in your head. And this is definitely going to be very resonant with the themes that Nancy talked about. You could think of it as part 2 or maybe part 0 of the same talk, and also connecting to a bunch of themes that Laura talked about and others. And they're both collaborators along with a number of really excellent students and postdocs whose work I'll single out when I talk about it. In the spirit of our Center for Brains, Minds, Machines and the mission of this conference, I want to start off with a clear success story. One you heard a little bit about yesterday on the neuroscience side. You'll hear more about tomorrow on the machines and theory side. But there are places where ideas, mathematical, computational ideas, have really had great value spanning across these different fields. So neural networks, for example, is one of these ideas that's been getting obviously a lot of attention in our fields and in the press recently. The idea that somehow neurally inspired mechanisms going back to at least Hubel and Weasel can be instantiated in machines that actually do useful machine pattern recognition that can be related to human behavior, to brain responses. It's an incredibly powerful idea. It's like we wouldn't have this meeting or a center if not for the progress that this field has arrived at. And again, as we all know, professionally, but also all of us in our daily lives and in the press, we've seen the re-arrival of AI as a serious thing. All sorts of AI technologies that we're beginning to take for granted or we'll soon have to take for granted and deal with, like our self-driving cars. And these are all impressive accomplishments. At the same time, we have to recognize that none of these systems are truly intelligent. None of them have achieved the original dream of AI. Another way to put it from a human cognition point of view is humans can do all these things, maybe not at world-class level, but they can do all these things, mostly in a self-taught or unsupervised way, and we'd like to understand that the computational magic of this flexible, general-purpose intelligence, which emerges even in very young children. So one way to frame the big picture of what this work is trying to get at is to ask, well, what else do we need besides, say, the ideas instantiated in both classic and recent neural networks? And one way to put it is that intelligence isn't just about pattern recognition. What neural networks have really focused on is what we could call pattern recognition, and that field is becoming more and more, we could say, a solved field. But intelligence includes many other things. Just one of them is what we could call modeling the world, and that's really the theme that drives a lot of the work that I'm talking about, as well as my colleagues who you've already heard from. So in addition to recognizing patterns, we have to be able to explain and understand what we see. We can imagine things we haven't yet seen. We can solve problems and plan actions to make those things real. And we can build new models of the world as we learn. Okay, so this is the general thing I'd like to understand. The specific modeling abilities that this research program is focused on is what I like to call the common sense core, which is a set of, let's say, mental modeling and model building abilities that emerge extremely early in infancy. The idea that I'm calling the common sense core is one that builds on a number of different fields. It's not my own idea or my work. It's inspired maybe more than anything by infant researchers, like, for example, Liz Spelke, who's also a member of our center, though she couldn't be here, Renee Bayer-Jean and others. Again, you saw Nancy give a little bit of an overview of that infant intuitive physics work, or intuitive psychology work by Gergely, Chibra, Amanda Woodward, many others. This idea that from almost as early as you can look, infants seem to perceive the world not just in terms of pixels or even high-level convnet features, but in terms of physical objects, intentional agents, and their causal interactions, a kind of intuitive theory of physics, and also an intuitive theory of psychology. Today I'll be really focusing on the intuitive theory of physics, although there'll be a little bit of a hint in the slide about the intuitive psychology, and you saw a lot of that at Laura's talk. The idea of this naive utility calculus is basically that version of this part of this research program. These intuitive theories of physics emerge early. They're, to a large extent, shared with other species. So Liz Spelke likes to say that basically pretty much anything that 5-month-old infants or younger have been shown to do, you can find in non-human primates and maybe some smart birds. Yet these abilities are enriched and extended massively in humans once language comes on the line. And they actually are the foundations of much of distinctively human cognition. Really, I like to think of it as the glue of cognition. So the targets of vision and other perceptual modalities, the basis of action planning, and the original seeds of a lot of linguistic meaning. And you're going to see more of that today and tomorrow. I think the people who asked Nancy about embodied cognition or the other kinds of simulation or emulation approaches, I think there's a lot of resonances, which I look forward to talking with you guys more about. So the research that I'm working on here is to try to understand these questions here. How are these intuitive theories, how can they be represented computationally? How can we study them rigorously, quantitatively in behavior with, ideally the kind of precision of psychophysics that we've used to, say, test neural network models. How can they be instantiated in the brain, and how are they built through some combination of evolution and learning and development? So you saw these abilities, as Nancy talked about, various kinds of scene understanding things, and that's also the setting in which I've been studying these with my colleagues and students. So scenes like the ones on the left, where you don't just see objects, but you see really interesting physics. A lot of things that could happen or are about to happen, imminent disasters. You can see the nails in that house being framed there, even though, you can't see the nails, but you know where they are, and if I asked you to point to them, you could say where they have to be so that the whole thing isn't falling over. Or these scenes of social interaction here on the right. Again, you don't just see people, but you almost see, it's as if you see into their minds. Again, ideas that Laura was talking about. And again, to resonate with my colleagues, I think you can study basically all of the important stuff in children, younger than kindergarten even, preschool and even infancy, particularly looking at how kids, say, play with simple toys like blocks and play with each other playing with blocks. So my part of this program is to understand these ideas in engineering terms, reverse engineering. And I put this slide blank with a question mark because I've been fascinated by these ideas since I first learned about them in grad school, but I feel like we haven't, until quite recently, had the engineering tools that are up to the task. As I'll try to argue in a little bit, I don't think neural networks on their own are up to the task, although I do think they can actually play an important role in this program, not just in pattern recognition. I've been sort of a closer starting point is work that I and many others have worked on, what you could call sort of probabilistic models, various kinds of Bayesian networks. These are ideas, if you're probably familiar with these, they look kind of like neural networks. The arrows often go in a different direction. They reflect a more top-down approach where the network is modeling the relation between a whole bunch of random variables and their causal interactions, and the arrows point from cause to effect, and they implement a form of Bayesian inference where you observe the effects and work backwards to the most likely causal interpretation. These tools, in many ways, can be used to build models of the brain's modeling engine, but they're not powerful enough, basically because of the graph problem. So the Bayes part is okay. It's the idea that you're going to define probabilistic models over graphs. Graphs are just not a rich enough representation to capture intuitive physics and intuitive psychology, or really anything that's there in common sense, I think. Instead, we've turned to what we call probabilistic programs. So these are strict generalizations of probabilistic graphical models, where the program it replaces the graph. The nodes and arrows have become literally something like the data structures and algorithms of a program. If you want to learn something about these methods, if you haven't heard of them, there's a nice web book that Noah Goodman put together. I helped out on this a bit, but it's really Noah's baby at Stanford. It's called Probabilistic Models of Cognition, or probmods.org. You could go to that. This figure here is from a nice review paper by Zubin Garmani that was in Nature last year, so you could check that out. Again, it looks kind of like a graph, but the key difference is that instead of having nodes and arrows, you have actual algorithms. So for example, the particular algorithms and data structures we're going to be defining probabilistic models on are inspired by game engines. Just curious, how many people know what a game engine is? Raise your hand if you know what a game engine is. Okay. Raise your hand if you have not heard of a game engine. Okay. And I'll take the other half to be the appropriate intermediate probabilistic middle ground. Game engines, for those of you who don't know or are unsure, are basically software tools that have been developed to enable people who want to design video games, in particular these kinds of games, like immersive three-dimensional worlds, maybe whole planets or whole galaxies that somebody's going to explore from a first-person perspective, to make it as real as possible, to allow the designer to focus on the story and the characters in this world, and not have to write everything from scratch, not have to write all the graphics, which is shared across all the planets you might ever visit, the way light might bounce off objects, and not have to, for example, model the physics. They can vary the particular physics that are in play, sometimes for interesting game effect. But they come with graphics engines, physics engines to model a wide range of physical interactions, not with Newtonian precise accuracy, but they're designed to simulate physics, for example, in ways that look good and can work very, very fast on a large scale to model all the physics going on in these worlds. They also have simple kinds of planning things. And indeed, I think this is just a sketch of the probabilistic programs that we've been suggesting for the common sense core, where I'll mostly focus on what's going on the left, the physics engine and the graphics engine, but game engines also have simple kinds of AI systems. Like, for example, if you want to put a non-player character in your game, like who's a guard that's going to patrol some base that a player is maybe going to try to take over, you might tell that guard, you might give him simple perception and planning abilities like you see on the left over there, or the right. Like, for example, if the player comes into your line of sight, then head towards him and try to shoot him. And you want to just, a game designer wants to basically just say that and not have to specify every detail about how the agent moves his legs and moves his head and so on. And I think that in some sense, these kinds of basic abilities for modeling the way scenes give rise to images, graphics, the way objects move through scenes dynamically and with forces, that's what's going on in physics, and the simple kinds of game AI, I think that's a good first pass hypothesis about what might be there in infants' minds, our basic common sense models of the world. So I'll talk about how we've been studying this in intuitive physics mostly. I'll tell you a little bit about, this is some of the background that Nancy kind of went over quickly, some work that Battaglia, Peter Battaglia, who's now at DeepMind, and Jess Hamrick, who's also temporarily at DeepMind for the summer as an intern. Normally she's a PhD student at Berkeley. We did this work a couple of years ago where we were trying to do sort of the psychophysics of physical scene understanding. So we gave people these blocks world scenes, and we built the following kind of probabilistic program model, which has both a vision component and a physics component. The vision part is basically taking an image and trying to approximately invert the graphics process. So to go backwards to something like a 3D CAD model that's necessary to run one of these approximate physics engines. So given that image there, we're going to be making, our model makes basically a rough guess at the 3D object structure that would give rise to that image under a standard kind of graphics projection. That's one hypothesis of a possible 3D thing. I'm showing the wireframe to suggest the 3D character of it. Now that is the input to one of these physics engines that does a sort of hack on Newtonian mechanics to approximately simulate a few time steps of the complex multi-body interactions of these objects under gravity and friction and collision and so on. So you run this physics engine a few steps forward and you get something like that. That's the world state after a few time steps. And the idea is that to make a judgment about whether a stack of blocks is stable or which way it's going to fall and so on, you do this. You first make a guess at the actual three-dimensional physical objects, and then you make a guess of what's going to happen under some approximate physics, and you look at the answer, you query it. This is one sample, a posterior predictive sample in our probabilistic physics engine. Here's another sample, and notice they differ slightly in the state estimate, which is not a perfect process, and they also differ then slightly in how the blocks fall. I mean, slightly, well actually they differ hugely. I mean, the actual state in the upper right there, and in this sample and that sample are totally different at the micro level. But at the macro level, you might think of this as a kind of intuitive statistical mechanics or something. At the macro level, basically the same thing happened, namely most of the blocks fell over. And so our model says, well, you run one or a few simulations like that, and you look at what happened, and you make high-level judgments based on the basic thing that happened there. And it turns out that that model, with only a very small number of parameters over and above the basic structure of the approximate physics engine, but basically a couple of parameters which describe the strength of different kinds of probabilistic uncertainty you might have, gives a very nice quantitative model of a whole bunch of different intuitive physics judgments. So this is just an example of data from one of our experiments. On the y-axis, you have the average judgments of a group of subjects, basically on a scale of 1 to 7, but normalized to something like the expected amount of the tower falling. So dots on the high end, people saying the whole tower is definitely going to fall over. On the bottom end, no, it's stable, and in the middle, some of it might fall over, I'm not sure. And on the x-axis, you see the average judgments of our model, basically the expected value of a small number of probabilistic samples from what I showed you there. I won't go into the experimental method details, but you saw a little bit of it in Nancy's talk. I'll just highlight the contrast between that graph and the one in the lower right there. That's the same thing that you would get if you used not a probabilistic physics engine, but actually the ground truth physics engine. So if you knew perfectly the state of where the objects were, and you knew all the forces in play rather than having some uncertainty, as this model does, that maybe somebody might bump the table or some wind might come along. It turns out that the ground truth physics does a much worse job. The correlation in our probabilistic physics engine is about 0.9. The correlation in the lower right there is about 0.6. And the reason is basically what's going on, let's see if I can get my arrow here. In this quadrant, you see there's a bunch of points here messing up the nice correlation. In particular, this red dot, which is this stimulus here and others like it. This is a tower which I'm sure to most of you looks unstable, looks like it should be falling over when you say turn on gravity, as our experiments do. But in fact, it's actually stable. The objects are balanced just so to make this thing stay up. But we might call this a physics illusion. And there's a whole bunch of physics illusions like this that this model explains in this category here, where basically it's an asymmetry where things that are actually stable can look unstable to us because generically, under the sort of random perturbations that come from the fact that our sense data is noisy, our perception is noisy, and our physics isn't perfect, generically this should be falling over. So I'll come back to that physics illusion in a bit. What I want to do now is show you one other kind of task that we've done, which is designed to address a number of criticisms or objections you might have. You might say, well, how do we know you have some kind of physics engine here that you can simulate all these different towers with? Maybe this is just the kind of thing that since we were kids, we've been playing with blocks, making these kind of judgments. Maybe we just learned, stored a lot of experiences and can somehow access those through some kind of associative memory or something like that. So let's try a task which, unless you've seen this talk before, is not one that you've done, but we'll do it here as a little bit of a demo. It uses the very same physics engine in our model, and I would argue in your heads, but it's not a task that you've had a lot of experience with. We call this the red-yellow task. So here's the task. I've got some blocks on this table, and the idea is imagine that the table is bumped somehow from some direction, hard enough to knock some of the blocks onto the floor. The question is it going to be more red or yellow blocks on the floor? So let's try it out. Would you say red or yellow? More red or yellow? Red, okay. Here? 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 Oh, red or yellow? Yes, of course. All right. So you can do this all day long. We won't do it all day long, but you can, right? So how are you able to do that? Well, what I would argue, again, is that you're using the very same kinds of thing that you were using in our task. You're running the same kinds of simulation. You're now adding in an extra force, which is some kind of bump. And you might be very uncertain about the magnitude or the direction of the force, but you just add that in to the rest of the gravity and friction and collisions and so on you have. You run a few time steps and you just kind of see what happens. So here's an actual window into our simulation. This is a simulation with a small force bump. Here's a simulation with a big force bump. And again, you can see the details of what happens are quite different, but you only have to run it for a few time steps, and that's important. I don't know that you could necessarily run these rich mental simulations in any detail for more than a few time steps, but you only have to run it for a few time steps here in either case to see what's going to happen, which is most of the blocks that fall to the floor are going to be yellow. And this model, again, is able to predict people's judgments with basically the same quantitative precision in this novel task as you saw in the other task. We can keep making things more complicated, so we can make the blocks different shapes and sizes. We can, in different trials, add constraints like walls on one side of the table or another. We can tell you the force direction, or we can leave it open. And again, the models basically fit well in all cases. It gets a little bit worse here, but basically these models are capturing the first principal component, which is most of the variance of what humans are doing, the majority of the variance. And the very same model doesn't just do these tasks, but you can ask it questions like, which way will the blocks fall, as Nancy was looking at, maybe how far they will fall. That one's pretty hard for people, and we have reason to think that's one of the few tasks that we've studied for which you probably are not using this model, but some kind of simpler heuristic. We can give you extra information which digs into the physics. So we can say, suppose the blocks are these two different colors here in the upper right, and suppose the gray colored blocks are 10 times heavier than the green blocks. Well, notice that's going to change your judgment in those two cases of which way the blocks are going to fall. But the geometry of the blocks are the same. We've just recolored them. So it's a nice kind of controlled experiment that shows that you have some cognitive penetrability into the mass part of your physics engine. Another kind of thing is we can show you towers like this, which in many cases look like they should be falling over, but suppose some of these are actually stable. They don't fall over when we turn on gravity. That might be a cue that some of the blocks, one color is much heavier than the other. And it turns out people can do that too. Or you can use the same kind of knowledge to plan actions like in this cool video game that Peter came up with, where basically you have to put the minimal amount of glue down to make these configurations stable. Of course, as you also saw in Nancy's talk, these aren't the only kinds of visual intuitive physics we can study, and we can also basically take the same kinds of ideas and apply them to something like, dots or balls bouncing around. So in some nice work that Kevin Smith did, oops, wait, let's go back, sorry. Oh, I gave away the answer, but not really. Okay, in these kinds of displays here, think of like looking at an air hockey table or a billiards table. You're looking down from the top. You're seeing this thing move. It's going to bounce around for a while. The black things are obstacles. And there's these red and green patches. And you have to make a judgment of will it hit the red or the green one first. And because it just sounds better, instead of saying red or green, just shout out ooh or ah. So, and you can update your predictions at any time. So we'll watch this, and just make a guess of which one it's going to hit first, red or green. Say ooh for red, or ah for green. Okay, ready? Here we go. Yeah, cool, okay. You were right. Initially, it looked like it was going to hit red, right? But then, after you realized, okay, there's this period of uncertainty, and then, a few seconds before it actually hits green, you realize that. So we can model this, but with the very same kind of probabilistic physics engine, right? But now we have to have a model of bounces. So it turns out that when there's collisions, in particular when an object hits an immovable thing, there's more uncertainty than just when it's just moving on its own, just with its own momentum. And we put that in, and then basically we can make a model which models the sort of cone of uncertainty. You can see its integrated predictions over there basically fitting what you're doing. And over literally hundreds of random configurations of this kind of thing, you can see here, I'm just showing 4 of hundreds that Kevin Smith looked at. You can compare people and models, that's the top and bottom plot, and they're really quite similar. It turns out even infants can make these kinds of predictions. So in some work that was mostly done by Erno Teglis and Luca Bonatti, and Ed Vool and I just added some models to it, they gave infants much simpler versions of these same kinds of sort of bouncing ball tasks. These are 12-month-olds. They showed them, for example, these 4 objects, like say 3 yellow and 1 blue bouncing around inside this gumball machine here. And then at some point, the scene is occluded, and then after a delay, maybe 0 seconds, 1 or 2 seconds, one of the objects appears. In this case, it was the rare one, the blue one. And they manipulate the length of the delay, whether it's the rare or the common object, and how close that object is to the entrance at the time. And I won't really go into the details again of the experiment, but the impressive thing, and they really had to work hard because they didn't have the thing that Laura was talking about that Kim Scott is building, this online scalable infant experiment paradigm. They had to run lots and lots of infants in the lab to get 12 data points, but they were able to show one of the first quantitative effects in infant looking time. So this is, the standard way that we assess infants' expectations is by seeing what they're surprised by. They look longer at things which are more surprising, that violate their expectations. But these guys were able to show a kind of graded probabilistic expectation in looking time by varying these spatial temporal factors across 12 conditions. And we were able to fit that. Actually, we had made these predictions. It wasn't even really a model fit. We came to them with predictions in a very similar experiment, and they said, it turns out we've already run 10 of the 12 conditions, and so we just had to wait a little bit, and then we had a very nice plot like this. We were able to predict this with basically a very simple kind of probabilistic physics simulation. Now, so I've tried to lay out the case for this physics engine in the head and something about how you could implement it computationally with the idea of a program that's a probabilistic program that captures your uncertainty about the world, and show you how we could study this quantitatively in adults and even infants. What are some other alternatives, and can we start to ask about how this might be learned, which is really the most interesting thing maybe going forward for a lot of us here. Well, one alternative, again, is to say, could we take a pattern recognition approach? Like, could we take the kinds of deep networks that have been so successful recently for things like object detection, and could we get them to work for this task? And some very smart colleagues of ours, not direct collaborators, although we're talking about some interesting joint efforts, at Facebook, led by Adam Lehrer and Rob Fergus, have taken on this challenge. So they've built a network that's called PhysNet, and it's a kind of convolutional neural network that basically is trying to predict the next frame in these block scenes. These are examples of some of its predictions and actions. It's trained on a very large number of simulated scenes from a physics game engine. And it also impressively generalizes, so they trained on these scenes of 2 to 4 cubes stacked up. They make judgments of will the stack fall over, and it can generalize to some extent to actual real photographs of real cubes. The problem is, from our point of view, is they have to train it with quite a lot of data, at least so far, several 100,000 examples, and it's only doing 2 to 4 cubes. It can do 2 cubes, 3 cubes, and 4 cubes. But you can do 10 cubes, 20 cubes, not to mention all the other shaped objects that there are in the world, not to mention all the other judgments besides will it fall or won't it fall. So this model has really yet to prove that it has the kind of scalable generalization that your intuitive physics does. But it's an open question, right? And it also interestingly fails to make those physics illusions. So you could say that's either a good thing or a bad thing, but it doesn't have the kind of sort of instability biases that people have, which I think are products of the actual probabilistic part of your physics engine. It's an open question whether with enough and more diverse training this can capture your inferences. And we and also Emmanuel Depew and colleagues, and Emmanuel's actually closely collaborating with these guys. I think we're all trying to work together to make challenges in data sets like the ImageNet or some of the speech challenges that Emmanuel talked about. We're hoping to make a first workshop where we all come together to talk about the right ways to push this general research program forward at NIPS this year. So if you're interested, talk to us. We'd love to have more people involved in that. There's also, again, I'm not against neural networks here. I think they're not going to be enough to capture the core of a physics engine, at least in their current form. But in our group, we've been exploring all sorts of different ways for neural networks and, say, probabilistic programs to interact. So in some very cool work that Jajin Wu and Ilker Yildirim presented at NIPS last year, in what we called Galileo, they've been exploring one way that neural nets and physics engines can interact by having a system that can look at these scenes of, say, an object sliding down an inclined plane and colliding with another object, which gives you information about the physical parameters of those objects, their mass, their coefficients of friction. And they combine a simulation engine like this thing here, which if I can play this video. So this is a sort of, they track the objects, and then they try to reconstruct the collisions in a simple physics simulation. But they also use a deep network to look at the static images, the static appearance, the same kind of things that we might do in an object detection system, to look at the shape, roughly the shape, the size, the material properties as realized in the visual texture, to make a guess at the underlying dynamics parameters, mass and friction. And then that becomes kind of a bottom-up proposal for a top-down, bottom-up inference loop, where they project that back down to see the dynamic predictions. If they've made a good guess at the mass and friction, then you can guess how the objects are going to move. You track the motion, compare that with the predictions of the physics engine, and you update the whole thing. And it's very much like the model that somebody was pointing out, the Kalman filter model. Where's the guy who pointed that out? Yes. So it's kind of like that, only it's not a Kalman filter, it's a physics engine. Because it's not linear, it's complex. It's okay. In some other work that we've been doing, again, to resonate with some of the themes in Nancy's talk, we're really interested in how, more generally, a physics engine might feed back to visual scene understanding. So remember the scene she had of reaching for the lime or something like that. In many of these scenes, your ability to know what's in contact with what, or what's there that you can't see. Think about all the pieces of fruit you can't see, but you know are there. Really has to be based on the idea that these scenes are probably stable, and what has to be there in order to make it happen. Or like these scenes here, anybody seen this kind of cool street performer illusion? These are examples from various European squares where these guys look like they're levitating. It looks like there's some missing object supporting them. Again, why is there a missing object? Well, because our physics engine is telling us there's got to be something there that I don't see, and you really can't see it. If you don't know how this trick works and you want to know, well, first try to figure it out, and if you can't figure it out, I'll tell you tomorrow. It's very cool. Okay, we've been exploring this kind of physical scene parsing in a number of ways, although I see that I only have 5 minutes left. So instead of telling you about this, I'll just say if you're interested in the ways we're exploring using physics to detect hidden objects, ask me about it, and I'll show you some cool experiments that are just in progress that Ilker is doing together with Max Siegel. I want to just turn for my last few minutes to the question of learning, which is mostly forward-looking, right? Can we understand, if you do have something like a physics engine in your head, how can we learn it? What kind of programs, if you like, if everything's a program in cognition, what are the programs that build other programs? In this case, the learning programs that build your physics simulation programs. So the starting point for being able to study development in this area, as Nancy referred to, is some great classic work by Bayer-Jean and Spelke and a number of others, looking at the development of these kinds of abilities over the first few months of life. And we'd like to understand, can you describe the states of knowledge that infants have at different points with a sequence of these probabilistic programs, maybe tuning or tweaking some of the parameters. That's maybe learning in this case. And then can you describe something about the learning algorithm as some kind of, at least somewhat rational search through the space of probabilistic physics programs? So this is something that Tomer Ullman, this is Tomer over here, he's one of our postdocs in attendance, there he is over there, if you haven't met him. So he's been exploring this in a number of ways. One is that he's pointed out some really interesting correspondences between the approximations that physics engines make in order to simulate complex interactions very generally, and some of the kind of curious things that infants do. Like infants seem to distinguish between moving and static objects. They're very interested in certain kinds of events like collisions. They often have a geometric object which is different from the physical object, and often in some sense, they're more interested in the physical properties of how an object moves through space and time than they are in the details of shape and color and texture, all the things that computer vision has been interested in. Seems to come in much later, but a sort of simpler physics object that is what you need to actually simulate the kind of physics we're talking about seems to be present much earlier. And very intriguingly, Tomer has the idea, which we're still just trying to work out what would mean, that we might be able to explain a lot of the puzzling, interesting things that go on in infant cognition by saying that in some sense they come equipped with some kind of a physics engine, and then learning is somehow sort of programming your mind's physics engine. One way to start in on this project is to ask whether kids, at what stage or age do kids actually have a unitary physical parameter like mass? And Tomer's been looking at this by building some really cool animations here, which sort of show all the different ways that in a physics engine, mass has implications for what's going to happen. Like heavier things make a bigger splash in water, or heavier things, of course, knock over towers, heavier things resist a particle or a wind of particles more. And he's been showing that, at least insofar this is just in older kids, like 3, 4, 5-year-olds, they do seem to sort of put all these things together into a coherent understanding of mass, and we're starting to see how you could ask these same kinds of questions in infants. We're also asking about the learning mechanisms. So there's an idea, another really important idea in developmental psychology is the idea that children's learning isn't just a kind of data analysis, but an active process of exploration and theory building. You heard a lot about this from the previous talks before lunch. And we're interested in how that plays out with these physics engines. So here, what this kind of comes down to, as I already was gesturing at, is this idea that learning physics might be something like kind of coming to the world with a game engine, but then sort of programming the game engine in your head to fit the experience of the particular game that the world confronts you with. Here I'm just showing examples of, these are basically a whole bunch of different games that they're all built with basically the same game engine technology. Check out, for example, the Unity game engine if you're interested. And it's really quite amazing how many different kinds of games you can build as a game designer using the same kind of technology. So I think this is a view of cognitive development in the context of, say, learning about the physical world, which is a really interesting mix of nature and nurture, right? And on the one hand, nature is building in a lot if it's building something like this in. On the other hand, there's a huge amount of flexibility and plasticity if you think about what you can do with this representational space. And we're just basically excited to try to explore this. So one thing that Tomer's been just playing around with, basically, is ways in which you might model some of the developmental trajectory that we've seen in, say, René Baillargeon's work in looking at infant development of stability concepts by basically saying you start off with one of these physics engines and basically sort of vague, uncertain knowledge about the forces that are in play. And showing that you can at least roughly model the sequence of stages that infants seem to go through by just kind of tuning and sharpening up the parameters, learning more about how gravity works, and learning that certain other kinds of things that you might have been open-minded about, like maybe things can be attached to other things, sort of unseen forces, learning the unseen forces, learning exactly which unseen forces might be there and which ones aren't, basically. The very last thing I'll just sort of gesture at is, to connect back to Nancy's talk, is in the brain. So Nancy gave you some of the evidence, again, very preliminary, that you have something like an intuitive physics engine actually in the brain, and maybe something about where it is. But then this just raises, I think, the really hard challenge that she mentioned both experimentally, and I'll just talk about the computational one, which is how could this actually work in neural circuits? So we've been starting to talk with Hamrick, for example, about how to actually study in single cell recording mechanisms that could do these kinds of physical predictions. But from a computational neuroscience point of view, it's a huge challenge. How could you build something like a neural physics engine, right? I mean, I think the Facebook guys were making a start at this, but really, we just don't have a clue, basically. Where people have been, I think, making the most progress right now is on various kinds of recurrent neural networks. So this is an example from actually work that's almost 10 years old by Sutskever and Hinton, where they built an interesting kind of recurrent temporal Boltzmann machine, and basically showed that it could, to some extent, model 3 balls bouncing around in a box. But it's just 3 balls, and it doesn't even do it really all that well. More recently, there's been some nice progress by Roland and Misevich and others, and I'll just point to the in-progress work by a really bright undergrad at MIT, Michael Chang, who's been working with Tomer and others to try to build a kind of neural physics engine. And the particular tweak here is that it's object-based. So it's not just trying to model pixels, but it distinguishes objects and their interactions, and it tries to use a neural network to learn something about the way forces work, but it assumes that there are objects and that they interact with each other in something like a F equals ma type calculus. I think Peter Battaglia and Jess have been pursuing similar kinds of ideas at DeepMind, but since it's DeepMind, we won't know until it comes out in Nature. But that was a joke, sort of. But what you can see here is that Michael has shown that, that this kind of works. So you take some of the kinds of like bouncing ball stimuli, and what you can see here is, if we just watch this from the beginning, on the top you see the ground truth, and on the bottom you see the neural simulation. And what you can see is that for the first second or two, it's pretty good, and then things diverge, right? It's a nonlinear system, and so uncertainty is going to magnify exponentially. Here's a similar thing where the next one was a system trained on 3 or 4 objects, and you can see it generalizing to 5 objects. And again, for the first couple of seconds, it seems to capture things, and then its predictions become detached. But this ability to predict a couple of seconds into the future, remember that's exactly the task Nancy was studying in this limited setting of bouncing balls, and it does seem that to the extent that we have a physics engine in the brain, it's good for about 1 or 2 seconds, which is the time span of sort of in the now action planning and thinking and perception, and I think that's the right target. So this is cool. Whether this could scale up to all the physical scenarios we've seen is a huge challenge, and I think it's going to require some fundamental new kinds of neural computational elements, but that's an open question, and we can debate that later. So just to wrap up, I've tried to argue that there's this core of common sense that we've been missing in our computational, cognitive, neural, and AI accounts until now, but that we have the beginnings of an ability to try to tackle, to try to understand how intuitive physics and intuitive psychology might work computationally, be realized in the brain, and learned. And this could easily, I think, take me for the rest of my career to really figure this out, and I think with many smart people working on it, we'll be lucky if we really crack this. But if we do, we might really have something like a computational model of common sense, and really the heart of human intelligence begins here. The tools that we've been building involve probabilistic programs and also various kinds of neural networks, because if we want to understand how this works in the brain, it's got to be some kind of neural network. But it's really open how to really even push forward the engineering tools to make the scientific vision here real. So if you're interested in this, I hope you'll work on it either on your own or perhaps in collaboration with us. Thank you.